Ça nous mène, cette petite introduction pour la structure nous mène à la première axe, c'est Prevent. Et dedans, nous avons Mariana, nous avons Zainab, nous avons Manel, et nous avons Hassan. Et without further ado, je suis heureux de donner la parole à Mariana.
Hello, my name is Mariana Segovia, and today I'll present a joint work with Zainab Rahal and Joaquin Garcia Alfaro, and it's about how to design and implement digital twins. So what we did is a state-of-the-art of how other researchers build digital twins, and we also applied it in an application scenario. So in this presentation, we are going to start with the context of this research. Then we are going to review the 3 steps that we proposed, which are design, modeling, and development, and then the final conclusions. So let's start with the introduction. In the last PhD day, I finished with this same slide because I wanted to build a digital twin for the testbed that I used during my PhD. So that's why we started to analyze how to build this digital twin. And basically, we have a virtual object that maps behavior of a physical object. This means that the physical object can send information to this virtual object, and then we can simulate and analyze information to control better the physical object. So there are many applications of digital twins, but some of them are, for example, to use all this collected information to optimize the behavior of the system, also to reduce cost or to improve the efficiency. Another application is also to predict future behavior of this physical process using the data, or to simulate different case scenarios to, for example, help making decisions at the business level. And of course, another possibility is to use it to improve the security of the system because it helps to improve risk assessment, also detection and mitigation techniques. So this is the process that we use to build the digital twin. First, in the design, we analyze which are the system requirements and which is going to be the architecture of the digital twin. Then how to model this behavior that we want to reproduce in the virtual environment, and how to integrate different models. And then in the development part, we have different tools, how to synchronize the information and communication protocols. So we apply this methodology to build 2 digital twins. One is a cyber physical digital twin, and the other is another project that we are starting with, and Zainab is going to talk about this in the next presentation. And I'm going to present the cyber physical system digital twin. So the first step is the design. And in a digital twin, normally we have like many components, and it's a complex process. So we are going to, when we do the system specification, we start with a macro analysis that we set the objectives and also the functional requirements. And then we start doing a micro analysis with designing the process plan. So normally in a digital twin, we want to reproduce one phenomenon or some of them, not all the possible functionalities that we have in the real system. So the first step is to choose which is this phenomenon that we want to reproduce in the virtual environment, and that determines which functions and also which equipment we have to map in the digital twin. With this also, we have to model which data we are going to consider and how to use it in the different models of the system. Another step is to also analyze how the digital twin is going to interact with the different roles that may be in the process. For example, operators, engineers, managers, so to determine also this interaction. So at the end of this step, we have different objectives, use cases, also the process that we are going to control, different states and metrics to monitor, the roles, and also some technical specifications. In the case of the cyber-physical testbed, the process that we wanted to control is this testbed with 4 water tanks, and we wanted to control the level of each tank, water tank. So the objective was to test new security approaches in this testbed and to monitor behavior deviations. So for that, the metrics that we choose is the quadratic cost and also the energy of the system to analyze first the correctness of the signal and also the loss in effectiveness that we may have in energy. And another point is that we wanted to test the 2 systems, for example, a production version and another version that we may have a different security configuration or a new approach. So we run in both the physical and the digital twin different versions of the software. Another aspect to consider is the system architecture. And here there are different architectures, but most of the researchers use one of these 2 options. The first one is a layer architecture, and the minimal configuration that we may have is just to have the physical object, the virtual object, and a connection, usually in real time because between these both components. And the other is to extend this architecture by adding, for example, a security layer, also data storage, modeling and optimization, a service layer which has all the AI applications and data-driven analysis, and also data visualization. And the other option is to use the RAMI 4.0 architecture, which this architecture is a common understanding of different industrial use cases that can be adapted to different industrial applications. So this approach is interesting because different digital twins may interact if they use the same architecture, and it also proposes like different layers of the digital twin and also different levels of interaction between the physical object and the virtual object. So in the testbed that we create, we use a minimal architecture. I know this is a simple scenario, but for example, imagine that here we have a production system and we want to do some tests. We cannot run a different configuration or a new approach in this scenario. That's why we create a digital twin which models this same configuration, and we run there the new version that we want to test. Like this, we can, for example, also feed information from the real scenario to test it in real configurations. And then we have a model to analyze both signals and detect if there are differences. With respect to the modeling, there are different types of models, but the main features that we want to introduce or to analyze is the structure of the system and the behavior. With respect to the structure, for example, we can analyze physical properties such as the formation of the object, also the corrosion, different physical properties. And in the geometry, we have, for example, the 2D or 3D models that analyze, for example, the size, the location, the shape of the figures. And then for the behavior, we have 2 main approaches, which is using physics, which we can model the behavior analyzing the processes that we have in the physical in the physical process, and also database analysis that collects this information and creates a model of this approach. And then these two approaches have different advantages and disadvantages, and that's why we have hybrid models that use both of them. So in this case, we use a physics-based model. During my PhD, I use mostly this kind of modeling, and this one, all the maths are explained in this paper, and we implemented it using Kalman filters. With respect to the development, one of the most important factors is the network connectivity. And different components have different requirements in terms of connectivity. For example, sensors and actuators are lower power devices, so that send also information at specific rates or when event happens. So it's better to have lower power consumption protocols. Then for the data gateway, we want protocols that aggregate information, and between the physical and the virtual object, the most important feature is to have a real-time connection. And for that, there are three main approaches. The first one is to use a low latency technology, like, for example, optical fiber or also 5G networks. Then we can use also compression techniques to reduce the data that we are going to send. For example, with AI, data filtering, or traditional compression techniques. And the other approach is to use edge computing to move the computation closer to the physical object. Another point is tools. Researchers and also industrial have proposed many tools, but the three that are most used in the papers are Eclipse Edito, which is an open source platform to build IoT digital twins. Then we have Figuear, which is also open source to manage data for digital twins. And then we have MATLAB, which is a classic for modeling and simulation. And another point is that augmented and virtual reality are quite used in this kind of scenario because they help to create this human-machine interaction between the digital twin and the humans. So in the case of our practical scenario, we use just Ethernet. We build the testbed using Java controllers, Raspberries as their TUs, then ultrasound sensors, water pumps, and the digital twin we use MATLAB because we already used this tool before and we have the models. But also we are trying with Eclipse Edito. We are doing some tests to integrate that into the platform. And to conclude, digital twins are really powerful in order to help optimizing the system and also to help in the business decisions. In this presentation, we talk about how to build them and also one application scenario. And another point is that digital twins are based on technologies such as AI, IoT, big data, and 3D visualization techniques. And without this, the power of digital twins would be reduced. And the main challenges that we found out during the state of the art is that first, how to validate the models, because models need to be accurate with the physical object, but in the literature there are not many analyses about how to test, how to tune, or how to calibrate the different models. Another point is how to integrate the information of a digital twin into a control system, because traditionally we have the control system which is calculating information in a loop, and how to incorporate this data is something that we didn't find in the literature. That's why most of the approaches only use a one direction connection and not bidirectional exchange of information. And the other point is that we are using AI to analyze all this information, to create the models. And we know that AI have vulnerabilities, in particular to injection attacks. And we have to find out techniques to protect this algorithm, and that especially may be running in critical infrastructures. So these are the references that we use during this presentation. These are our publications. And I want to thank you for the attention. And if you have any question.
Very much. Do we have questions in Paris? You can think about it. I will maybe start with the first question. How much can you automate the creation of such a digital twin? Because if I understood correctly, you did it quite manually in the sense that you looked at the models, the differential equations or equations that you could put. But when you look ahead of that now, are there parts that could be automated? If you think about it, did you find something in the literature? Is it something interesting to follow? And side question, which leads to that question, is how complex was the creation of this digital twin?
Mm-hmm. That's a really interesting point. Thank you for the question. Yeah, I think that so far it's like intensive, like human intensive, this activity, because we need to like to put the effort to analyze which are the parts that we want to translate into this virtual representation and how to translate this data. So far, yes, it's quite manual. I think that maybe with machine learning, we can like try to create more automated design. I didn't analyze how to do it yet, but it's a really interesting point that we may analyze further.
Thank you very much. Do we have additional questions? Marco?
The model you created or you wrote, are you able to simulate visually and predict some kind of behaviors? I'm sorry, maybe the question is answered in the.
Normal. It's normal. Well, these models are based on the fluid flows. This is just equations about the physics, like how water moves. This is just physics. That's why I used the calculation that were in the paper.
Actually, my question is, if I can rephrase, did you implement the model?
Okay. Yes, we can simulate it also. Yes, there are also simulations that we can see. There are MATLAB simulations. After, if you are interested, we can share, for example, these simulations. But yes, it's actually, this is a picture of some simulations that show how the water increases or decreases. And yes, it's implemented with command filters using different parameters, because these equations here are, for example, the different configurations of the tanks, like the properties, the dimensions, and the hole size and everything. So we translate like this equation using the configuration that we have in the real test bed with the tanks that we have, and we can reproduce that in simulation and also in the real environment.
It's a shame. I think it would be interesting or impacting to have a GIF or something, an animation, little animation showing that you actually implemented.
Okay. Yeah. Okay.
Okay, so if there are no more questions, there's a question.
It's Cyril. Thank you a lot for this presentation. I would like to know how do you imagine to be able to discriminate failure behavior from a cyber attack?
Well, for that is not an application that I have so far analyzed, but I know that there are other proposals that they collect data and using machine learning, they create different models to detect this kind of attack within the virtual object. But for example, what we are working, that Zainab is going to present a bit after, is, for example, how to improve the response in 5G networks using these digital twins. So for example, we can, in case of an attack, copy the state of this particular state in the digital twin, and then, for example, try different mitigation techniques or try different configurations and analyze which is the best option of the best response that we can apply to this particular situation, for example. But I don't know if I answered your question, but yes, we didn't apply this particular scenario to detection, but there are different proposals to do this. And well, we can exchange information after if you want. And also Joaquin wants to say something.
Yes, I don't know if you can hear me. I was just wondering about the question. Cyril is a very good question, and something that we have been doing in the past, maybe during the time of the PhD of Mariana, but also in the other thesis of Jose, is that we were trying to differentiate a little bit like failures from attacks from the point of view of the nature. So the nature of a failure is more a probabilistic nature. So it follows more a distribution in terms of probabilities, when the attacks are following more kind of intentionality of a human, or especially the ones where the human is kind of involved. So of course we can separate malware or automatic code from human attacks. We think that the human attacks, or the ones in which the guy is still behind the screen, are much more complex and also much more powerful, so the intentionality is even higher. And we try to discriminate in this manner. Like failures are going to have really a probabilistic nature. It happens because often it happens, and you can have this distribution in terms of probabilities. The other, you can really have this intentionality that you can model with an attack graph or tools, and that will be the way how we would be differentiating this kind of two events.
Okay, thank you for your precision.
Okay, very good. Do we have another question? If not, yes.
I have a question.
Okay.
I was wondering, when you have the digital twin, how basically when there is a real system, is there a methodology to during design time to detect potential interactions that are not? How do you assess whether you cover all interaction between the different parts of a system? For a very small one, I can understand that the few equations that describe the components independently might be sufficient. But when you go for a large system, there might be interaction and so on. Is there a process to detect whether there are interactions that were not covered by the first version of the digital twin? Is there a process to check that the digital twin really match the interaction that are in the real system? That's my question. Sorry for that.
Yes. Well, in complex system, yes, this task is much more complex because we have first interaction between different components, and also normally we have like different phenomena that we want to that we may analyze. For example, mechanics, electronics, different factors that we may reproduce. So that's why in the beginning we have to choose what we want to do. For example, in the 5G digital twin, we have different phenomena also, like the antennas, like the physical components, also slicing. That's why, for example, we choose just to focus on slicing, because otherwise it's really complex to analyze that. And also there's this the complexity of integrating different components. First, integrating different models for a component, and for that, the strategy that normally is used is to apply different models sequentially. For example, if we have a component and you have the geometry model, then we have, for example, the network model, and then we have another about the physics. Normally we choose, for example, the order that we are going to apply the different models, and we apply it sequentially. Like this, we can test it in also like taking the outputs of one model into the other. Because when we have multiple models, for example, we may have information which is, if they execute in parallel, we have a problem that maybe the information is not of different models, they do not agree. So it's interesting to analyze this. And the other problem is the complexity of integrating different components to create a big system. In this case, we have to also, there are also techniques. Sorry, I can like explain all of them, but most of the integration are like hierarchical. So we start like with small components, and we integrate them to create more complex structures. For these are techniques, and then there are others which are more collaborative. So I don't know if I answer your question.
Yeah.
Yeah. Okay.
Okay, then let's thank Mariana once again.
Thank you.